name is Gianluca Baldassare, and I'm sharing this presentation together with Emilio Cartoni, who is online. And the presentation is about the REAL competition. REAL stands for Robot Open-Ended Autonomous Learning. And this is the second edition of the competition. And as we will mention later, we will have other sessions, other editions of this competition in the coming years together with ICDL. First, we start by giving the grand view of the idea that is behind the presentation, behind the competition. And then we get into the details of the competition itself and how it went this year. So the idea of the competition is to create a benchmark for open-ended learning that is so important and so well studied in the community of this conference. And a very important concept in open-ended learning are intrinsic motivations. The competition is divided in two phases. So there is this international competition where participants have to undergo two phases. The first phase where the robot is kind of thrown in an environment and it has to learn for a long time, let's say for a month ideally. And the idea is that the robot should learn as a child that plays with the environment and the objects in the environment and acquire skills and knowledge about how to interact with the environment. And then in a second phase, which we call the extrinsic phase, you can come back as the user of the robot and ask the robot to use the knowledge it acquired in the first phase in order to accomplish a goal that you desire. For example, you might tell the robot, look, there is a current state of this kitchen, which is very messy. So can you please make it similar to, can you please make the state of this kitchen similar to the picture on the bottom right? And you show the photo, for example, of the state that you would like to see the kitchen in. So that's the idea. The robot should learn autonomously skills in the first phase, and then on the basis of the knowledge acquired during the intrinsic phase, it can solve any type of task in this kind of environment. So the application potential of this technology, of this idea, is huge. Indeed, if you manage to create a controller for a robot that has this kind of capabilities I showed in the previous slide, then you can use the same software, the same architecture for the robot in different environments like these ones, for example, that are very different between them. And the robot in the first phase would acquire the skills dedicated and focused for the particular environment it's facing. And the algorithm would be the same. So that's why this solution has such great potential for application, has such big interest for robotics. So a little bit of the background where the idea comes from. As this conference, there is a strong inspiration from the way in which children and babies learn and to master the world. So for example, when we are little babies, first we explore our bodies, so we make sense of our being distinct from the environment. And then we start to explore single objects and their properties. And then eventually we start to investigate, explore more complex situations. And all of this is driven by intrinsic motivations. And then when we are adults, we can use and exploit the knowledge we acquired by playing when we were children in order to accomplish things that are useful for our biological survival or to gain a wage as workers, let's say so. So the knowledge, the mechanisms that are there when we are babies and child and kids that drive our learning are there because evolution understood that it's good to allow ourselves to acquire knowledge and skills when we're young, and then to reuse these skills and knowledge later on when we are adult for example, biological purposes. So the REAL competition wants to be a benchmark that defines in an operational way this kind of ideas. I have to say that I spent years investigating these kind of problems. And I remember there were always discussions about how to measure the fact that a particular system is good or not to acquire knowledge independently, to acquire skills independently. So the idea of this competition was to try to formulate the first benchmark to operationally define and measure the quality of different robotic systems to undergo open-ended learning. That's important because, as you know, in machine learning or robotics or computational sciences in general, it's very important that you can compare different algorithms in order to understand which ones are better and for which reasons, and so that you can improve. So that's fundamental for the advancement of the of any discipline in machine learning and robotics, autonomous robotics. So we devised this competition, and it's based on a simulated robot. Emilio will talk a lot about that. Basically, it's a KUKA robot simulating on the basis of bullet, a physical simulator very fast. It has a gripper with some sensors, and the robot perceives the environment from the top, as you can see at the bottom right of the screen. And there is a table with a shelf, and there are some objects on the table, 1 to 3 objects. And so how does the competition measure the quality of the knowledge that the robot acquires independently in the intrinsic phase when it explores for a long time the environment? It does in this way. So imagine that in the specific competition, we have 15 million steps. So that's the time where the robot is a child and can freely explore the environment. And the crucial thing about this phase is that there are no goals, no rewards, no guidance whatsoever from outside. So just 15 million steps during which the robot can do whatever it wants, okay? In order to get familiar and learn as much as possible about this environment. Then in the second extrinsic phase, the robot is called to solve a particular set of problems, actually. And each problem has this structure. There is an initial state, and as you can see at the bottom right of the screen. And here, there is an initial state with a particular configuration of the objects in the environment. And then the robot is shown a goal, so a different configuration of objects. And its task for this particular goal is to bring the state of the world from the initial condition that is in front of the robot to the goal condition. So for example, it has to move this object on the shelf or out of the shelf or in different places. And during the extrinsic phase, the robot has to solve 50 goals like this. And the important thing is that in the initial intrinsic phase, it was not aware of which goal it had to solve. So this is just a quick snapshot of the possible initial conditions and the possible goals that the system has to face. And Emilio will explain the different typologies of goals that we can have during the extrinsic phase. And here, before passing the word to Emilio, I want to clearly define the problem. We managed to do this definition, this formal definition only recently, and I think it's very interesting because it clarifies the challenge that is behind the competition. So basically, we have here again the structure of the competition in 2 phases, the intrinsic and the extrinsic one. And the important thing is that the utility function that describes the problem for the robot is defined only in terms of the extrinsic phase. And the reason is that I will go through some details about this equation because it's very clarifying, I think. So in the extrinsic phase, I said that you have a certain number of extrinsic goals to solve, let's say 50. And for each goal, the robot is challenged by the goal and has to solve it. And it has a measure of performance. And this performance is subject to noise because the policy of the robot is eventually noisy. And the policy of the robot has to be goal conditioned. So depending on the goal, the robot has to do different things, right? So it has to take into consideration the desirable state that the environment should assume. So it has a policy that produces action on the basis of the current states, of the goal that the robot wants to achieve, and the policy has some parameters, okay? And we compute the average of this performance over 50 goals, and that's the average. So there is a particular sampling, basically this 50 goal represents a possible sampling of the possible goals that the robot should be challenged with in this environment, okay? But other possible goals might be drawn. So the average gives the average capability of the robot to manage this scenario. And the problem of the robot is to find the parameters of the goal indexed policy in order to maximize the performance over these goals. So the critical point is that this is the cost function, the utility function the robot has to pursue, but the parameters have to be found during the intrinsic phase when the robot knows nothing about the goals it's going to solve in the extrinsic phase. So if you wonder, how is it possible that it can learn to do things that are actually known only afterwards? The answer to this question is that the environment is the same. It has the same structure. So the robot has to explore the environment in order to acquire knowledge about this environment and about its object in a general way, in a possibly as general as possible way, so that in the extrinsic phase, it can solve the tasks that we assign to it. That's the only link, the only link that can allow the robot to transfer knowledge from the first to the second phase. The stability of the environment and its regularities. So to link this kind of challenge with other similar tasks defined in machine learning, there is meta reinforcement learning, which is probably the most similar one. And here, the robot or the system, the intelligent system, is challenged with a given set of tasks. And by learning this set of tasks, this given set of tasks, it has to generalize and become able to solve new tasks in a later stage. Okay, so compare this kind of problem with our problem. So the problem that I just defined, the problem of open-ended learning. So here, in the first phase, there are no tasks to learn. So the system has to self-generate them based on intrinsic motivations, on self-generated curriculum learning, and so on and so forth. And the idea is that by doing this, the robot has, again, to generalize and be able to solve any type of task that can be drawn in the second phase in the same environment. Similarly to what meta reinforcement learning does, but with a big difference that in the first phase, the robot has to self-generate the task, whereas in meta reinforcement learning, the set of tasks is given. Okay, I think I finished, yes, my part of the presentation, so I pass the word to Emilio. Emilio?
Thanks, Gianluca.
Yep.
Can you hear me?
Yes, I can hear you. Yes, you can
Great.
start.
So I'm Emilio Cartoni. I work with Gianluca at EST CNR of Rome, Italy. And so I will now talk about the current edition of the real competition. Can we go to the next slide?
Yes, actually, I am already in the next slide. Can you see? Can you see it?
Next.
Interesting. Okay. Also, I don't see your face. I don't know if it is my fault or. Do the other people see the face of Emilio?
No. Maybe no.
That's switched off. It looks the same as it did for you.
Yes.
And now we see.
Okay.
It.
Now we see Emilio, but Emilio, can you see the slide switching?
Yeah, now, yes.
Okay, great.
Okay. Great. Yes, I can see that.
Okay.
So the competition is an online challenge. So it's hosted by AICrowd.com, and there you can see the link. And we had the first round from August to October, which was just a warm-up. And then we are having a second round starting in a few days in November that will run up to February 2021. And then there will be a short final evaluation round in February. And the real competition is hosted this year by ICDL, and also we have contacts for the next 2 years. And so we'll present the results at the conferences, and there are prizes related to the conference. Indeed, some participants of round one got free registration for this conference today. And then, so as Gianluca said, why a competition? To establish a benchmark to compare open-ended learning approaches, and then to foster research and new solutions to the many problems of open-ended learning. And we will talk about the different challenges in the latter part of the presentation. So how does it work? There is this simulated robot with the arm and the gripper. And then it has, the participants have to create a controller that learns how to interact with the objects on the table. There is a first phase when the robot has to freely explore the environment, and then a second phase where the robot is given some tasks that are unknown in the first phase, and then the performance is scored, depending how close the robot managed to place each object to the goal position. And then the controller with the highest score wins. So, okay, so this is the environment. And as we said, it's KUKA 7 degrees arm. And there is a 2 degrees of freedom gripper with touch sensors. There is also an invisible camera from the top. And then there is a table with these 3 objects. And the robot can be either controlled in the joint space, so each joint individually, or it can be controlled in Cartesian space or with a predefined action. And we'll talk more about it later. And so next slide. We have different type of goals in the extrinsic phase. The first type of goals, we call it 2D because they are on the plane in the first part of the table. And then we have a second class of goals where the objects can also be on the shelf, so in the farthest part of the table. And in both these 2 categories, the objects have a minimum distance between each other and they keep the same orientation. While in the final type of goals, objects are, can be in any part of the table and can even be one on top of each other and can have any orientation. So in this sense, it's called 3-dimensional. And then the score is the average of all the individual scores obtained in each of these 50 goals, which are divided 25 are 2-dimensional, and then we have I think 15 two-dimensional and goals 3D. And then in the next slide, we can see how the robot should look like during the different phases of the competition. If you start a controller that does random joint actions, it will usually look like on the left. So totally untrained, it does not know anything. So it just wanders around with apparently meaningless movements. And then at the center, it's an example of controller that comes directly from our baseline algorithm that is available in the competition. And it looks a lot more structured, in part because it used a predefined action, and in other part because it has already learned how to move the object, and so it frequently interacts with it instead of going around. And then on the right, you have the ideal controller that hopefully somebody will be able to develop by the end of the competition, that perfectly knows that to achieve the goals, what is needed is to grasp the object and bring them around without interfering with each other. And that will be the perfect controller. To participate, the competition, I didn't say it, but the software is in Python. And it is possible to download the environment, which is a gym environment from that first link. And then we have also a starter kit that includes both a baseline algorithm, so to get participants started, and also it contains the software to upload your solution to the iCrowd.com for the evaluation. So how to participate? You can download these 2 things, then you write your own algorithm, you test your controller on your computer, running both the intrinsic phase, so a long phase in simulation where the robot learns, and then the extrinsic phase when the robot is given the 50 goals. And then when you are satisfied, you can submit the controller to the online servers of AI Crowd that will run again the extrinsic phase. In both the first round and second round, so the one that is starting now of the competition, you have to upload your code and also some files, depends on how you structure it, with what your controller has learned. So for example, if your controller is some kind of neural networks, you will upload the code, including the weights of the neural network. And then the AI Crowd will only run the intrinsic phase. However, at the end of the competition, there will be a final evaluation where we will run the code starting from your code starting from 0. So it will be tested both the intrinsic and the extrinsic phase. The intrinsic phase lasts 15 million time steps, so quite a long time. And in the extrinsic phase, as we have said, you have 50 goals to achieve, and there are limited time to achieve each goal, 10,000 time steps, so a lot less compared to the intrinsic phase. So it's still possible to learn something during the extrinsic phase, but the time is very limited. So the robot has to learn before. Then there are also some computational limits. In general, your algorithm should be able to run the intrinsic phase and the extrinsic phase within those time limits, 72 hours and 6 hours, on a fairly powerful machine. And then participants should follow, of course, the rules. And the golden rule is basically to follow the spirit of the competition. That is that the robot should not be told what the task will be. So the robot should learn from scratch during the intrinsic phase to interact with objects using intrinsic motivation, self-generated goals, and so on. And it's forbidden to tell in advance the robot what the goals will be. For example, using the scoring function of the intrinsic phase or some similar variants. So, for example, it is forbidden to create a reward that explicitly rewards the controller for moving its arm towards the object right from the start. It has to learn it by itself or using more general functions. Okay. Then we, compared to the previous year, we have introduced many simplifications. All of these apply to round 1, and then we have decided to apply most of them also to round 2 because it's a very difficult competition. So you have the choice to control the robot in joint position, in the joint space, so moving all angles of the arm and the gripper individually. Or you can use position control, where you can say the X, Y, Z position of the wrist of the arm, and then specify the quaternion, that is the orientation of the wrist, and then also specify the 2 degrees of freedom of the gripper to say if it's open or closed. Then participants will also be able to have special hard-coded home actions that brings the arm back to the initial positions. And then participants can choose, every time they submit their code, they can choose if the environment they want to face contains 1, 2, or 3 objects. Having less objects is, of course, easier. It's easier to start with 1 object, but you will score less points during the extrinsic phase, because the final score is the sum of the scores that you obtain for each object. So if you have only 1 object, you have only 1 score for each goal. Then you can elect to keep your gripper constantly closed all the time, which of course, on one part it's a simplifications because the interactions are more easy, because you don't care about the gripper anymore. But of course, with the gripper course, you cannot, you have no chance to grasp the object. And so for some of the goals will become impossible. For example, it's very hard to move one of the objects on the shelf without grasping it, but only eating it. And in the same spirit, you can keep the, you can elect to keep the wrist orientation fixed vertical, which makes easier contacts on the table. So the environment is more under your control, but this also limits your possibilities. And then in round one, we had the participants could use, instead of the joints or position control, could use a predefined macro action, which basically was a push movement along 2 points on the table. And we will see that later, because the baseline was created using this macro action. So again, as I said, we had just a warm-up round that finished a few days ago. And then starting in a few days, we will have a second round. And at the end of the second round, the top 10 will advance to the final evaluation, which will happen in February 2021. There is a mistake in the slide. And it will last only 1 week. And each of the top 10 participants or groups will have a maximum 3 submissions during the week, and their code will be evaluated by running both the intrinsic and extrinsic phase. And also I want to remind that among the rules, there is the code inspection. To be eligible for ranking, participants are required to open the code must be visible to the organizer, because so that it's possible to verify that indeed the code learned by itself and did not contain like argued and information and the controller knew about the goals beforehand. So the round one has just finished. There were 47 people subscribed, but only a few managed to submit their solution. And as you can see on the right, the first classified and second classified actually made less than the baseline. On one end, they used the, they did not use the macro action. So they actually faced a more difficult challenge. And they achieved more than a random system, which would achieve 0.02. But still, as you can see, the score was very low. Consider that if you can achieve the precise position of each object, of free object, you would gain a maximum score of 3. And with perfect position of one object on the first plane, you would have to achieve roughly basically the 0.25, so basically the baseline. So this means that it was these solutions did not achieve to position correctly even just one object. So it was the challenge is still very hard despite the simplifications. Okay, so I encourage you to face this challenge. I hope the difficulties will make you want to show that your approaches. I hope some of you are now thinking, oh, I can do a lot better, and will participate. And the top 3 teams will be invited to co-author a paper. And we will also have free registrations and discounts to ICDL 2021. And also we are working to add more prizes, and that will be announced later during the round 2. So why is so difficult to achieve the goals? Well, there are a number of difficulties. These are the biggest ones. Let's see them. So the first problem is that that random exploration rarely touch objects. This year we have reduced the joint space and the Cartesian space, the maximum space allowed. So it's a bit more frequent to touch the objects, but it's still very rare. Even the macro action, the one that we used in round one that had a predefined push moment along the table, would hit the table, would hit an object like only 1 on 5 actions. And while the joint space, which I think is the hardest one, usually moves like in the GIF that you can see on the right. So basically wanders off. And so how one can make the robot concentrate on touching the objects, which is the most significant part of the environment. One possibility is to use, for example, intrinsic motivation to guide the exploration. And one example that we also gave in our competition page is the articles from Patak. And this one from 2017 and also others more recently published, where the exploration is guided by the ability to predict what will happen. So by the prediction error. So we may suppose that if one uses this kind of motivation to get exploration, the robot will probably focus at first on predicting the image of its arm. Where will it go when I'm doing these commands? But after a while, it should be able to predict its own arm, which will become boring, so to speak. And when it will hit an object, then this will be unpredicted, and it should then focus on hitting the object. So that's a possibility. Then another problem is that the robot does not even know that the objects exist. And one possibility to learn the existence of the object is to try to train a variational autoencoder on the images. We did try this, and we saw that when you apply the variational autoencoder to the images of the table with even one object, the latent variables that encode the image after the training on the variational autoencoder have a correlation with the position of the object on the table. So basically, just from the images, the variational autoencoder is able to learn that there exist two variables, which for us are basically the X and Y position of the cube, for example. But to train a variational autoencoder, you need a variety of images. And so this is an obstacle. And also there is the fact that when the objects move, there is also the object, the arm on the image, which is also very big. And so if you collect the images with the arm in it, the latent encoder will have a big incentive to track the arm first. And it may not learn about the objects if they are too small. Then the other obstacle is, of course, that it has, during the intrinsic phase, it has so much time, but it has no rewards and no goals. So what you should learn about, and how do you self-generate some tasks to practice so that the robot in the end has an ability to control the environment. And two possible solutions that we mentioned is NAIR, the article by NAIR, Visual Reinforcement Learning with Imaging Goals, that actually learns first an autoencoder, so it encodes the environment with the latent variables, and then from the variational autoencoder, it tries to, it makes a sampling and draws a new latent images, so to speak, and it tries to achieve them. So it imagines some goals to practice. And another interesting article was the one by Florenza, because it also tries to learn a separate network that gives you not just any goal, but goals of intermediate difficulty, so that you do not try again a goal that is too easy or that is too hard to reach, because that would, of course, waste your time. And then the other problem is that these three problems, that is learning about the objects, generate your own goal, and learn how to control the objects, they all interact. For example, the first problem about learning about that the objects exist requires a variety of images to properly train the autoencoder. But to have a variety of the images, you need to move the objects. But to move the objects, you have to know that the objects exist. And so it is kind of circular. And this makes solving the challenge more difficult, because you have to do many things at the same time, and they all must work together. So the algorithms that you would apply should also be able to learn with unstable representation that learn through time as you learn more things. Or you should have at least, I mean, you would have to learn in multiple phases. Maybe I try to learn this first, I learn a bit, then learn another thing that is on top of this, and then I learn again. So they have to interact. And also one of the possible solutions is to clearly separate all these problems into different models, into different responsibilities. So to have some kind of the architecture that coordinates the various models. And that's what we did with our baseline. So indeed, we created a general architecture with these components. So we had an abstractor where there was a variation autoencoder, then an explorer that tried new actions to gather new knowledge. Actually, in the baseline, we just put some random explorer. So that's probably the easiest thing to improve if you start from the baseline, which again, I say that it's available with the software of the competition. And then there was a planner for the control for the final phase that that combined all the actions tried in the past and kept in the memory with the abstraction to achieve the goals. And I think that I have summarized also this next slide, but yeah. As I said, in the abstractor, there was a variation autoencoder. In the explorer, for now, it was random with the predefined actions. And then the planner was an A star, and with also some abstraction that we just invented for the competition that tried to make a progressive abstraction. This, in practice, this means that you had a set of actions in the memory, and if no actions seemed good to make a plan, it tried to merge the actions, giving the actions, the state of each actions, which were encoded through the abstractions into latent state. Let's say a bigger radius of states that he thought that they would apply to that actions. In a sense, the progressive abstractions made the planning problem progressively more relaxed to try to achieve at least one solution. And then we have, okay, now we have a video of the baseline. Okay, there was also some kind of music that we cannot hear. So there was the first intrinsic phase where it did did a lot of random actions, about 15,000 random actions. And sometimes it got lucky and it could move the cube. And most of the time, like 80% of the time, it just moved in the empty space of the table. So this is certainly one of the models that can be improved the most. And then we should have about 30 seconds of random actions in this video. And then there is the extrinsic phase. So on the upper right, you can see the goal. The robot during the extrinsic phase beyond the state of the environment receives this extra observation, that image that you can see of the goal, which is the same type of image that it receives for the current state, but it has the desired goal. And then, as you can see with the planned actions, in generally, it could achieve the goal most of the time, sometimes trying more than once. And okay, so we are about at the end, I think. I think we have to click outside the video, and then, yes. Okay. So for the future, as I said, we have already an agreement for real 21 and 22 with ICDL, which I thank. So thanks to the organizer and to the chair of next 2 years, Luo and Jamone. We are open to collaborations, so if you want to join us, you have ideas on how to improve the competitions. And then we also seek sponsors for additional prizes. In particular, we would like to support the travel expenses to the conference, hoping that next year we will be able to have conference in person. And so the challenge is open. Get ready for round 2. I hope you will all participate. And I think, okay, there's no next slide. So thanks, and question time.